You, Miss Pat Addison. Welcome everyone, and again, thank you for joining us once more for your Friday Happy Math Hour. Um, as Miss Heidemann mentioned, for those who are here to review your math class or Math 1324, go ahead and click on the link, and we will start shortly. We'll give a few seconds for those to transfer over to the Math 1324. Very well. So again, today's topic is exponential logarithmic properties. So we began with exponential logarithmic last week. So we're going to continue, but please feel free if you have any questions, you need us to review some of those important fundamentals for both exponential logarithmic, please put them on the chat or go ahead and raise your hand and ask. Okay, so let's go ahead and get started. So on these new sections, which is basically from your chapters 3.3 and 3.4 now, you're going to be asked to solve for a log functions. So just to do a quick review, again, a log is an inverse of an exponential function. It has a base, the input, and an output. Okay, so to to help us solve for these problems, what we can do is one of the easiest ways to solve them is to convert this log into an exponential equation or function. Okay, since our calculator is not able to solve for this automatically, we can use our math knowledge to be able to do this. So let's go ahead and again change this log equation into an exponential equation. So as I mentioned to you, this log has a base and its input is 125 and its output is x. And then what we reviewed last week is a log equation or function is the inverse or the opposite of an exponential function. So what I'm going to get is an exponential function that has the same base as this log of base 5. So I'm looking at an exponential function that has a base 5. But in order for me to convert it into an exponential form, I do everything backwards. So the input of the log is going to be the output of the exponential function. And the output of a log is going to be the input of the exponential function. So let me go ahead and show you what I'm talking about. So if we see here, the log of base 5 of 125, this is its input and this is its output. The same equation, but in exponential form, has a base 5, just like my log. And again, the exponent was the output of my log, and the input of the log is the output of my exponential equation. So now what we can do is we can do what we did last week. In order for us to solve for this, what we can convert is a 125, and we can use our 1-to-1 property. I can convert 125 into an exponential equation that has a base 5, and 5 to the third power is 125. So it's easy to see using my 1-to-1 property that for solving for x, x has to be 3 in order for these two exponential equations to be equal to each other. Okay. So again, this is, I believe, the best and easiest way to solve for these log equations. So let's go ahead and look at another one. So let's say that we have log of base 2 and my input is 25 is equal to x. So I'm going to convert this log into an exponential equation. So let me go ahead and do this. So my log given is a base 2. So I'm going to have an exponential equation that has a base 2. The output of the log is the input of the exponential equation, or its exponent. The input of the log is the output of the exponential equation. Now, let's see here. This one's a little bit more complicated because we cannot rewrite 25 with a base 2. So what we're going to have to do on this particular problem is use our calculator. And what we can do to solve for this is something called the change of base. And again, just to review, when you're looking at a calculator, your calculator only does logs, or if you have a scientific, only does logs of base 10. If we don't have a subscript down here, we automatically are assuming that this is the base 10. Now there is some scientific and some graphing calculators that allows you to change the base on a log. But normally, if you're not able to change the base on your calculator, it's assumed that it's a base 10. So how can we do this if our calculator does not have the feature to change the base? So what we can do is we use something called the change of base formula. And what this says is that given any base log, what we can do is we can go ahead and calculate it mathematically by applying these properties. So again, let's say that I have some base given. So to evaluate a log of any given base, what I'm doing is I'm going to take the log of base 10 of the input divided by the log of the base 10 of the base given. Okay, so to better understand these formulas is by doing examples. So let's go ahead and directly jump into an example. So let's go ahead and solve for these. Again, you have some homework problems on WebAssign that ask you to do this. Also, don't be scared on the wording. Sometimes your homework problem is going to ask you to use the ratio formula. And what that means is it's just that division that you want to do, change the base formula. Okay, so let's do A, log of base 3 of 11. So if your calculator does not have a form or a way to change the base, what we can do is do the change of base. I'm going to take the log of base 10 of 11 divided by the log of base 10 of 3, which was my base. And when I do this, my calculator can do this because it has the log base 10 feature. So log of base 10 of 11 divided by log of base 10 of 3 gives me 2.183. Okay, and this is just rounding to 3 decimal places. Okay, so how about this one? B of log of pi of 0.5. Well, we know pi is a symbol and represents an irrational number. It's a number that's 3.14, blah, 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 right? It keeps on going forever. But we can also use our calculator to solve this. So what we can do is we can do our change of base formula, saying that the log of the input of base 10 of 0.5 divided by the log of base 10 of pi will give us a value. And this answer is negative 0.606. Yes? And again, on this one, I rounded to also 3 decimal places. Okay. So whenever we are not able to use our one-to-one property or have to use a calculator in order to solve a log, this formula will come in very, very handy. And it's called the change of base formula. Okay. All right. So let's review a few of the properties. We did some already. We did the ones on the bottom already, the basic properties. But these are new properties that we have for this chapter or this new section, which is our product property, our quotient property, and a power property. Okay. So the first one, the product property, says that if I have a log and the input, I can separate it in two values that are being multiplied by each other. I can expand it into two different logs. I can expand it to the log of the base of one input plus the log of the same base of the other input. Okay. We also have the quotient property that it says that if I have a log that has the same base and I have two items that are being divided by each other or two elements that are being divided by each other, I can expand this into two logs, the log of the base of the numerator divided by the log of the same base of the denominator. And then we have the power property that says that if I have any log of same base and I'm taking the input to some power, some exponent, I can use my power property that says that I can multiply that exponent to my log. And again, the natural logarithms have the same properties. We just using natural log instead of the math log. Okay. So again, to better understand these, let's look at some examples. Okay. So it says use the properties of logarithms to rewrite the logarithm in terms of the log of base 5 of 2 and the log of base 5 of 3. So one, they're giving us already the log of base 5, but they give us this input 6. But I can rewrite this as a product. I can rewrite 6 as a product of 2 times 3, right? So I can say that this, the log of base 5 of 6, I can use my product rule and say that 6 is 2 times 3. And by using my product rule, I can expand this to two different logs. I can say that the log of base 5 of 2 plus the log of base 5 of 3. Okay? All right, let's look at another example. How about this one? says find the exact value of the logarithm expression without using a calculator. Uh-oh, not a problem. So first, what I'm going to do is let me rewrite this cube root to demonstrate that it's part of an exponent. That way I'll be able to use what's called my power rule, okay? So I can rewrite the cube root of 4 in this format, log of base 4 of 4 to the 1/3 power. Well, that's what the cube root in exponential form is. So now I can see that by applying my power rule, that I can multiply this 1/3 to my log. So this is going to give me 1/3 the log of base 4 of 4. Oh, but this is a fundamental property, right? Any log of a given base, and I have the same input, this value is 1, right? So the log of base 4 of input 4, if you can see, okay, is 1. And 1 times 1/3 is going to give me 1/3. So I'm able to solve these just by applying all of my fundamental properties without using a calculator. Okay. All right. So let's practice some more. Find the exact value of the logarithmic expression without using a calculator. Let's do the natural log. Natural log of the fourth root of e cubed. Okay. So the first thing that I want to do for the a is rewrite this as an exponential equation. So, or an exponent, right? So I'm going to have the natural log of e cubed to the 1/4 power. But now I have to also apply my exponent rule, that if I have an exponent to another exponent, I have to multiply these exponents. So then I'm going to have the natural log of e to the 3/4 power. Now I can apply my power rule that says that that exponent I'm going to multiply to my natural log. So I'm going to have 3/4 natural log of e. But then again, I see that natural log of e is one of my fundamental properties, that this is going to give me 1, right? So I have 3/4 times 1, so the answer is 3/4. Okay. And again, all these are steps using just my basic properties to solve for these logs without using a calculator. How about B? The natural log of e to the 4th power plus the natural log of e to the 8th power. Well, the first thing I can do is I can apply the power rule, right, to condense. I can condense these two, um, or well, let's do them separately. So what I can do is I can apply my power rule first, and says that this 4 I'm going to multiply to the natural log. This 8 I'm going to multiply to this natural log. So 4 times the natural log of e plus 8 times the natural log of e. And again, just as before, I know that the natural log of e will give me 1. So this is 4 times 1, and 8 times 1. So 4 times 1 is 4, 8 times 1 is 8, so 4 plus 8 is 12. Okay. All right, so let's look at this one. And again, if I'm going too fast, please stop me and let me know. Question says, use the properties of logarithms to expand the expression as a sum, difference, or constant multiples of logarithms. Okay, so what they're basically telling me is they want me to rewrite this as a multiple logs using my properties that I just learned. Okay. All right, so the first thing that I see on this one, given natural log of z times z minus 1 to the 4th power, is that I have an exponent, right? So I have an exponent of 4. So I'm going to use my, 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 actually, again, the order, we got to be careful on the order, but the first one, what we're going to do is we can do the product rule first. Okay, so I see that I have two things that are being multiplied by each other, right? So we have the natural log of z times z minus 1 to the 4th power. So I can separate these two logs. I can separate with the natural log of z plus, and I'm forgetting the natural log here. Let me rewrite it. Let me go one more, see if I corrected it before. And oh, there it is. It's correct. So I should have had here, let me write it. There should have been a natural log here, okay? So the natural log of z plus the natural log of z minus 1, which is right here. So then on this one, I can apply my power rule that I have an exponent of 4, so I'm going to multiply to my log. So it's natural log of z plus 4 natural log of z minus 1. Oops. And I'm done. This is it. This is my final answer. There's nothing else that I can simplify. So I went from one log to 2 logs on this particular one. Yes? All right, let's look at another one. Oh, I like this one. Okay. So we have again, the question says use properties of logs to expand the expression as a sum or difference and or constant multiples of logarithms. So here I have the log of base 5 and I have a quotient here. I have the square root of x squared minus 9 being divided by 4. Okay. Um, Now, so let's go ahead and apply our quotient rule. It says that when I have two things that are being divided by each other that have the same base, I can subtract them with two separate logs. So I can have the log of base 5 of the square root of x squared minus 9 minus the log of base 5 of 4. Okay, but we're not done. This first law can be simplified, and I know it can be simplified because again, the square root I can represent it as a exponent. So I rewrite the square root as an exponent. I'm going to have the log of base 5 of x squared minus 9 to the 1/2 power. So applying my power rule, I'm going to multiply that 1/2 to my log, and it's going to give me 1/2 log of base 5 of x squared minus 9. But again, I cannot stop here, and most students stop here. One thing that I notice here in this input, this x squared minus 9, I see that it's a factoring technique. It's a difference of squares, right? I have x squared minus 3 squared. 3 squared is 9. And I can convert this into a product. So this x squared minus 9 can be written as x minus 3 times x plus 3. Again, it's a difference of squares. So now I see that now I have a product for a same base. So I can expand this by using my product rule, right? So let's rewrite and use our product rule for this last part. Also, don't forget, we had that 1/2 to this log. So I have to carry that 1/2 to each of the individual separated logs, right? So the final answer is going to be 1/2 log of base 5 of x minus 3 plus 1/2 log of base 5 of x plus 3. And this came from my product rule, okay? And then I already had the minus log of base 5 of 4, okay? So questions, okay? This question is used a lot. You'll see this sometimes on exams, okay? So make sure you study it. All right. Let's look at this one, A. Still doing the same thing. Use properties of logarithms to expand the expression as a sum or difference. So let's do A. Log of base A, and I have the numerator of x cubed divided by y cubed times z to the 4th. So let's first apply our quotient rule. I have two elements that are being divided by each other with the same log. So I can separate it by expanding it by subtracting 2 logs. So I can have the log of base 8 of x cubed minus the log of base 8 of y cubed times e to the 4th. Okay. Oh, I see that the right-hand log has a product, so I can apply my product rule to the right side of the log. So this is going to be log of base 8 of y cubed plus the log of base 8 of z to the 4th. Please don't forget that because we have a minus in front of this log, we would have to distribute since we're separating or expanding it to two different logs. Don't forget to apply your parentheses here, okay? Because this minus has to be applied to both of these. This minus was applied to the single log, but now it's applied to both of these. So don't forget our parentheses. So we're almost done because the questions say that it has to be a constant multiple. So we have to get rid of our exponents. And to do that, we use our power rules, right? So let's go ahead and apply our power rules, or first let's distribute the negative that I was talking about, I guess. If you put the answer with the parentheses in the computer, it's going to mark it correct, but you can also expand it, okay? So let's just expand it since I already wrote it here. To expand this negative, a negative times a positive is a negative log of base 8 of y cubed. A negative times a positive is a negative log of base 8 of z to the 4th. Now let's go ahead and apply my power rule. And this means that this exponent of 3 gets multiplied to the log of the base 8 of x. The exponent of 3 gets multiplied to the log of base 8 of y. and the exponent of 4 gets multiplied to the log of base 8 of z. So my final answer is this. Okay. Again, I went from one single log to multiple logs with all exponents of 1. Okay. That's what that means, the constant multiples. All right. All right, let's do B. Um, we have a natural log. So we have the natural log of the 10th root of z to the 7th times x to the 5th plus 7. Okay. So first, let's rewrite this as an exponent so we can see the power. So we have natural log of z to the 7th times z to the 5th plus 7, all of this to the 1/10th power. Okay, so be very careful with our parentheses because we had the square root. The square root of 1/10 is being applied to all of my input. Okay, don't miss out any of these parentheses, or the computer is going to mark it wrong, or do something weird if you're using your calculator to solve. Okay, all right. So now that I have this, I can use my power rule, and that 1/10 is going to be multiplied to my log. Then I see that I can have a product rule. I have two things that are being multiplied inside the same base of my natural log. So I'm going to apply my product rule. This is going to give me 1/10 times the natural log of z to the 7th plus natural log of z to the 5th plus 7. Okay. What I can do is I can distribute the 1/10. And again, and I think if you leave the 1/10 outside on the computer for WebAssign, it's not going to mark it wrong. But let's just practice our distribution property. So my final answer is going to be 1/10 times the natural log of x to the 7th power plus 1/10 natural log of x to the 5th plus 7. Okay, now I can't move any forward here on this right one. Okay, and you might be tempted to want to do something with the right one. I can't. There's no properties that have a addition of the same base. Okay, it's only the product or quotient rule. The two terms are being multiplied, or the two terms inside the log are being divided. There's nothing that it has the addition. Okay, so be very, very careful. All right. So let's go ahead and oh, I can apply the power rule to the first one, right? I have a exponent of 7. That one I can do. So that applying the power rule to that one is going to give me 7/10 natural log of x plus the 1/10 of natural log of x to the 5th plus 7. This one again cannot touch it, but this one I did have an exponent that I can simplify using my power rule. All right. So let's do it backwards now. Let's condense an expression to a single log or a single quantity. So it's basically the same thing. We're just working backwards now. So the first thing you have to check before we start working on this is that for us to condense, we have to have the same logs or the same base. And I do, right? I have a log of base 6 here, and I have a log of base 6 on this one. So I am able to use my properties. So let's go ahead and do this in order. I see that on the right side of my log, I have a 9 being multiplied to the log of base 6 to x. So I can use my power rule that this 9 becomes an exponent, right? So I'm going to have log of base 6 of 3x minus the log of base 6 of x to the 9th power. Okay, so there's no more numbers that I can convert to exponents. So now I have just the simple logs. I have a subtraction. So this is the quotient property that says that if I have two logs that have the same base that are being subtracted from each other, I can divide them into one single one, right? Applying the quotient rule. So this is going to give me log of base 6 of 3x divided by x to the 9th. Okay, and this is my final answer. Okay. Questions? All right. Very good. Awesome. Awesome. So here, again, we can simplify, but there's really nothing for us to simplify. Yes? Don't forget. Um, oh, sorry, we can't simplify. We can factor out an x, right? Excuse me. Sorry for that. So the top numerator has an x, the denominator has 9x, so I can simplify one of the x. So one of the x's cancels, so the x from the numerator cancels with one of the x's from the bottom. So my final answer is log of base 6 of 3 over x to the 8th. Okay. All right. Let's do these two more examples. Okay. So I'll do A, and then what I'll do is I'll give some time for some of you guys to start working on B, and then we'll share work. Okay, so let's do A together. Condense the expression. Again, let me look at the logs. Oh, they don't have a base on here, or they don't have a subscript. When they don't do when they don't place a subscript on here, this is telling us that these are base 10. Okay, so whenever you don't see a number down here, it means automatically that we're dealing with a base 10 log. And they are all three of these logs are base 10, so I can start using my properties. So let's start in order. Let's start with our power rule. So you see that um, I have two logs that have a number being multiplied to those logs. So again, this is the power rule. So the 6 is going to become an exponent. The 7 will become an exponent, giving me log of base x minus the log of y to the 6 plus the log of z to the 7. Okay. Now, for me, the way I like to do them when I have multiple ones is just do like if I was reading an expression. I'm just going to work from left to right. Okay. So I'm going to start from left to right, and I'm going to look at first the log of base x, the log of base 10 of x minus the log of base 10 of y to the 6. These two logs are being subtracted, so I can use my quotient property. So I have this log of base 10 of x divided by y to the 6th power. Oh, now I'm left with two logs that have the same base of 10, but now this is the product property, right, or product rule. Now when I have two logs that have the same base that are being added with each other, I'm going to multiply um, the inputs. So then this is going to give me the log of base 10 of x over y to the 6 times z to the 7. And I can simplify just to make it a little bit prettier. And this is going to give me the log of base 10 of x times z to the 7th divided by y to the 6th. Okay, so very easy stuff. Hopefully, again, all it requires is for us to really know our properties. Okay, so let's go ahead and do B. And what I'll do is I'll give a couple of seconds for you guys to start it on your own, and then I'll continue and we'll compare answers. Hopefully, we're all on the same page. So I'll give a few seconds. Okay, I'm gonna go ahead and start working on the problem. Again, you guys continue working if you're working on it, and then again, we'll review together. Okay. Okay, so let's look at this. So the first thing that I see is that we are dealing with a natural log. Okay, so they're all natural logs, so I'm able to use all my properties. So again, whenever we have these brackets, we want to follow our basic math conventions, right? So order of operations. So since we have brackets, let's go ahead and do that first. Normally, if I didn't see any brackets on there, I would just do it from left to right, like I was reading. But since they put brackets, I need to follow order of operations. So let me do that first. So I see that in here, I have two natural logs that are being added to each other that have the same base. Again, these are both natural logs of base 10. So this is the same thing as the natural log of x plus 1 times x minus 1. Okay, now you can go ahead and do FOIL to solve this, but I also recognize that this is could be a difference of squares. But again, if you do FOIL, you're going to end up with the natural log of x squared minus 1. Okay, so then we got rid of the brackets because we did that first. So now we have two logs, natural log of x minus the natural log of x squared minus 1. This is our quotient rule or quotient property that when we have two logs of the same base, we subtract them. The first one is our numerator, the second one is the denominator, giving us the natural log of x over x squared minus 1. Okay, now also just to help you, I can't cancel this x from the bottom x. Okay, in order for me to cancel, they need to be factorable. Okay, so I can't factor an x from the bottom because it's attached to a minus 1. So my answer is like this. Do not touch it. That's our final answer. Natural log of x over x squared minus 1. And I know all of you got this answer, right, before I did. Um, so let's go ahead and move forward. All right, let's do some more of the solving, okay? Let's practice more of the solving that, we stopped on this one, 2x to some value that we can evaluate, right? So for me, the first one should be easy, right? I can convert it into a one-to-one um, um, exponential equation. So I know I can rewrite 4 as a base of 2. So that's 2 squared. So for these two exponential equations to be equal to each other, that's telling me that the exponents have to be equal to each other. So the answer is x equals 2, right? For these two to be equal. All right, let's do b. So for me to do b, what I would do is let me go ahead and use some of my properties in order to be able to solve this. So what I see is, or apply my one-to-one property, is move the natural log of 13 to the other side, right? And I do that by adding natural log of 13 on both sides. So this gives me the natural log of x is equal to the natural log of 13. So this one's hopefully a lot easier, and also I can use my one-to-one property that for these two logs to be equal to each other, the inputs also have to be equal to each other. So then x is equal to 13, yes? All right, how about C? E to the x is equal to 13, okay? So what I'm gonna do is I'm gonna use my, I call it my inverse property, right? Or you can say that you can multiply the natural log of, of the log on both sides, but um, I can do this. If I do one thing on one side, I can do it to the other. So if I multiply, let's say that I'm using this term multiply the natural log of both sides. When I do multiply the natural log of e to the x, is going to give me the natural log of 13. Okay, but on the left one, I have a product rule, right? Power rule, excuse me, that I can rewrite this as x times um, the natural log of e, and that gives me 1. So x is equal to the natural log of 13. So if I use my calculator, the natural log of 13 is going to give me this value. If I round this answer to 3 decimal places, it's going to give me 2.565. Yes? Again, I didn't write these, but I skipped these steps, right? Again, I applied my power rule, gives me x times the natural log of e, and I know the natural log of e gives me the value 1, hence why I had just x on the left side, okay? So again, if I'm skipping steps or going too fast, please let me know. All right, let's look at this one. Solve the exponential algebraically. Approximate the result to 3 decimal places, and if you have multiple answers, give it as a separated common list, okay? So what I'm going to do to solve for this one is the same approach that I did just my previous example, okay? So what I'm going to do is first apply my one-to-one property. Says that if I have two exponential equations, okay, I can, for these to be equal to each other, that means that the exponents have to be equal to each other, okay? So this is going to be x is equal to x squared minus 6, and you see that we're going to have a quadratic. So because I have a quadratic, I'm going to move everything to one side. So what I did here is I just moved the x to the other side by subtracting x on both sides, and it's going to give me x squared minus x minus 6. So again, there's multiple ways of solving this. You can factor it or use a quadratic formula. For me, I rather factor, okay? So I can rewrite x squared minus x minus 6 by this product, x minus 3 times x plus 2. And by using my zero property, I have two answers, either x minus 3 is equal to 0 or x plus 2 is equal to 0. Simplifying or solving for x, I have my two answers, either x is equal to 3 or x is equal to negative 2. Okay, and again, it's always good to double check your answers, plug these values back in to make sure that you have two equal expressions. Okay, all right. Let's look at this. These are a little bit more complicated because they're going to require an additional step. So let's start with the first one. Solve the exponential algebraically. So we have 5 times 3 to the x power is equal to 20. So the first thing that I want to do is I want to isolate the exponents, right? Or the exponential equation. So for a, the first thing I'll do is I'm going to divide both sides by 5. Okay. So let's divide both sides by 5. And it's going to give me 3x is equal to 4. Okay. Again, on this one, I cannot use my one-to-one property because there's no way that I can make 4 into a base 3. Okay. So what I'll do is I'm going to multiply the natural log of both sides. It's going to give me the natural log of 3 to the x is equal to the natural log of 4. Okay. Again, on the left side, apply my power rule. X times the natural log of 3 is equal to the natural log of 4. Solve for x by dividing both sides by the natural log of 3. So x is equal to the natural log of 4 divided by the natural log of 3. And on this one, I'll have to use my calculator. So when I plug it into my calculator, the natural log of 4 divided by the natural log of 3, this gives me this long number. But again, your homework is going to ask us to round our answer to 3 decimal places. So my answer is going to be 1.262. Okay. All right. Let's do B. So and again, let me have you guys start and we'll compare answers. Okay. All right. I had to connect my laptop because it was about to die. All right. So let's go ahead and solve for B. Okay, so again, we want to isolate the exponent. So let's go ahead isolate the exponent by adding 9 on both sides. So when we add 9 on both sides, we're going to get e to the x. Oops, this is should be not 27, but let me fix this. Let me see. Um, this should be 45, right? Because we're going to add 9 on both sides. So this should be 45. So let me see if it's corrected. It's not corrected. Okay, so this should be 45. This should be 45. So this is 45. Okay, so here again, I'm going to apply the same problem, the same rule that I did for my other problem. First, I'm going to apply the power rule. This is going to give me x to the natural log of e to the x. And for these two to be equal to each other, x is equal to the natural log of, again, this is 45. Let me do the correction, the final correction. Never got corrected. So this, let's see if I can do it. This should be 45, okay? And again, this came from this. I'm isolating e to the x. I have to add 9 on both sides, okay? And we subtract it. Okay, so 36 plus 9 gives me the 45. All right. Okay. Again, we can, oh, now it's corrected. Final. um, and so got corrected at the end. All right, so again, the x is equal to the natural log of 45. When I plug it into my calculator, it's going to give me 3.807. Again, rounded to 3 decimal places. So the computer doesn't pick up all the corrections, right? All right. Let's do this one. Solve the logarithmic equation algebraically, approximate the result to 3 decimal places. Okay. So far we haven't had any where there's no solution. I'm not sure if we're going to get one of those, but we'll give an example of those at the end if I have time to see when we would have a no solution. Okay. So here um, we see that the natural log of x is equal to -4. So my solution here, again, I'm going to use my inverse property, or I can convert it into exponent. Okay, and to convert it to an exponent, what I like to do first is rewrite the natural log as a math log. That way you can see the base. Okay, so here I'll rewrite natural log of x using a math log. So this is the same thing. The log of base e of x is equal to a -4. And again, this is just a property that we should be familiar with. So now let's go ahead and do that. Let's convert this into an exponential equation. So my base is e. Again, the input of the log becomes the output of the exponent. So the input is x, so my output of the exponent is x. The output of the log is the input of the exponential equation. So here we can see that e to the negative fourth power rounded to 3 decimal places gives me 0.018. Okay. Again, our properties will come in very, very handy to solve most of these. And most of the problems on your homework are going to ask you, when they say algebraically, means that you're going to give two answers. The computer first wants to see this work, e to the negative 4 equals 2x. And then it's going to have the second part to do it using your calculator to evaluate this. Okay, so most of these questions will have two answers, especially when they say algebraically. All right, let's go ahead and do these two. Solve the logarithmic equations algebraically. And then, again, the second answer would be approximate the result to 3 decimal places. So let's do A. 2.8 is equal to the natural log of 3 to the x. Okay, so the first thing that I'm going to do, just so you can see it, you don't have to. Again, there's ways to applying the logs, inverse logs automatically, but I also like to practice converting to exponential form, okay? Because you have a lot of homework problems that require you to do that. So let's just practice changing to exponential form. So the first thing that I'll do is I'm going to change this natural log to a math log, to the log of base e of 3 to the x. Again, the exponential log has a base e, so that's my exponential equation, base e. The output of the log is the input of the exponent. The input of the log is the output of the exponent. So we have e to the 2 to the 8, 3x. Okay, so I'm going to divide both sides by 3. So this will be your first answer, okay? Algebraically, this is the answer. E to the 2.8 divided by 3 is equal to x. The second part, rounding to 3 decimal places, is applying our calculator. First, I'm going to do e to the 2.8. Then I'm going to divide that by 3. It's going to give me 5.482. Again, rounding to 3 decimal places. Okay. All right, let's do B. So to do B, the first thing we need to do is, again, we need to isolate the log. So let's go ahead and subtract 5 on both sides. So this is going to give me 11 minus 5, which should be 6. Okay. Then I'm going to divide both sides by a negative 5. So we have here the natural log of x is equal to 6 divided by negative 5. That's the, well, um, we haven't solved for x. So the first thing we do is, what we can do is change it to exponential form so you guys can see it. We have the log of base e of x is equal to 6 over the negative 5. Converted to exponential form, e to the negative 6 over 5 is equal to x. Again, this is the algebraic answer. The numeric answer or estimated answer is 0.301. Okay. All right. Let's look at these two. So keep on practicing solving logarithmic equations. Okay. A, natural log of x minus the natural log of x plus 6 is equal to 7. Okay. So for me, what I would do before I get started, I'm going to condense the left side. Now that I have some new properties that I can use to get only one log. So I'm going to apply my quotient rule because I have two logs that have the same base that are being subtracted. So that's my quotient. And that says that it's the same thing as a natural log of x divided by x plus 6 is equal to 7. Okay. So I can change it to an exponential form. This is the log of base e of x to the x divided by x plus 6 is equal to 7. Let's go ahead and convert to an exponential form. This gives me e to the 7th is equal to x over x plus 6. Okay, so one thing we can do is you can cross multiply since we do have a proportion, or we can just do algebra. What I like to think of and also help my students, because sometimes they always want to use cross multiplication to solve fractions, but they only work when I have this scenario, when I have a proportion, when I only have an equal between them. Okay, so I'm going to cross multiply, and it's going to give me this. Okay, e to the 7 times x plus 6 is equal to x. Okay, I'm going to distribute first the e to the 7, okay? So it's going to give me e to the 7x plus e to the 7 times 6 is equal to x. So what I'm going to do is I'm going to combine all the x's or put all the x's in one place. So I'll have all the x's on the left, anything that has an x on the left, and any numbers on the right, okay? So let's do this. So I have e to the 7x minus x and minus e to the 7 times 6. So if you see, what I did is I moved the x to the left and I moved the e to the 7, 6 to the right, because that's just a number, but I don't want to evaluate it just yet. But I need to solve for x. So what I'm going to do is I'm going to factor out an x from the left. So this is going to give me x is times e to the 7 minus 1 is equal to minus e to the 7 times 6. So to solve for x, all I have to do is divide both of these sides by e to the 7th minus 1, yes? So we have x is equal to negative e to the 7 times 6 over e to the 7 minus 1. So this is the algebraic answer. Let's go ahead and play it into the calculator. Again, also another something to consider. Um, your calculator, when evaluating, one way to do it is to do all these individually and then at the end divide. But if you want to do it all in one line, you got to make sure that you include all the right parentheses. Okay, you got to tell the calculator the order of operation, because calculators don't know order of operations. They'll just multiply whatever they see first. So make sure you use the right number of parentheses, and if you do, you'll get this answer, negative 6.005. Okay. Again, please let me know if you have any questions, comments. All right. So we always want to check our solution. Okay. So on this particular one, okay, we did have a problem, okay, that has no solution, right? So we got this answer, negative 6.005, but we want to check. And when we plug this in, okay, you'll notice that one of the x values is going to give us a negative value, right? Or both of them actually going to give us a negative value, okay? So as we mentioned in the last class, we cannot evaluate negative logs. We're going to get an error on our calculator. So on this particular problem, we're going to write no solution, okay? Because we cannot use negative values inside our logs or natural logs, okay? So we did have an example of no solution, okay? All right, so let's go ahead and do B. The first thing that I'm going to do, again, is apply my quotient rule to condense the right side. I see that I have two logs that have the same base that are being subtracted from each other. So to condense it, I'm going to divide them, right? So we have the natural log of x plus 9 is equal to the natural log of x minus 6 divided by x plus 6, okay? Now this just becomes a one-to-one property. For these two logs to be equal to each other, the inputs have to be equal, right? So I'm going to set my inputs equal to each other. X plus 9 is equal to x minus 6 divided by x plus 6. Again, I'm going to cross multiply. And when I do that, I get x plus 9 times x plus 6 is equal to x minus 6. Okay. If I distribute everything and simplify, okay, I have this. I got rid of the parentheses. Um, as you can see, I'm going to have a quadratic again. So what I'm going to do is I'm going to move everything to one side so I can have my simplified quadratic, right? So when I do this, okay, I am going to get x squared plus 14x plus 60, okay? Again, there's several ways to solving this. We can factor, or we can use our quadratic equation. So just so we can practice our quadratic equation, let's go ahead and use it. So to apply our quadratic equation, it's this here, okay? My A value is 1, my B value is 14, my C value is 60. When I plug all this in, okay, I see the root inside with the negative numbers. Go ahead. Someone have a question? Okay. All right. Yeah, and if you have a question, please raise your hand or put it on the chat. We'll get to it. Also, want to remind you guys, if you haven't done so already, make sure you guys click on the surveys and links so you guys can get credit for attending our class. Okay, don't forget to click on those links. Okay. All right. So again, see, I know we dealt with imaginary numbers, but on these particular ones, since we're solving, we're gonna have a no solution again because we cannot get the square root of negative 44. So this particular problem also will have a no solution as the answer. Okay. We did all this work just to come up with a solution, but don't worry, it's good math practice. Okay. Don't stress that we had no solution. Okay. And we're having fun. I hope we're having fun. All right. Let's go ahead and look at this one. Um, Solve the logarithmic equation algebraically and then approximate the result. So we have the log of base 9 of x minus the log of base 9 of x minus 8 is equal to 1/2. As you can see, we can condense the left side by using our quotient property. So let me rewrite this as the log of base 9 of x divided by x minus 8 is equal to 1/2. Okay. I'm going to use my change of exponential equations to solve. So I'm going to convert it to an exponent. So we have 9 to the 1/2 is equal to x over x minus 8. Okay. So again, I'm going to cross multiply to solve for this one again. Okay. So I evaluated the square root of 9, which gives me the plus or minus 3, and then I'm going to cross multiply. So here I'm going to have two answers. I have 3 times x minus 8 is equal to x, and minus 3 times x minus 8 is equal to x. Okay, so if we solve algebraically for both, we have 12, x is equal to 12, and x is equal to 6. But we want to check our work. Okay, we want to make sure that we have a solution for both, and we don't get a negative input for one of them. So if you see here, okay, when we use x is equal to 12, okay, nothing's wrong here. We have log of base 9 of 12 minus 9 of base log of 9 of 12 minus 8, which gives me 4. So this one is doable. But look what happens when you use x equals to 6. If we use x equals 6 on the second log, 6 minus 8 will give me a negative number. Again, this will give us an error. So x equals to 6 is not a solution. Okay, so the only answer that we're going to have for this one is x equals 12. All right. All right. So some of you will be having your exam next week. So we wish you the best of luck. Hopefully this session helped you a lot to understand a little bit more this chapter. Again, if you have any further questions, um, I want to invite you. We have tutors that are happy to help go over more materials more slowly, or you want to do additional problems, please go ahead and ask. Again, thank you for joining us. Again, wish you the best of luck. Thank you so much. Don't forget to click on the links to get your attendance for attending the session. Again, thank you all. Goodbye.
Thank you, Mr. Carizales, for your presentation. We want to remind you all about our previously recorded sessions, which are available on a YouTube playlist. This session will also be available on that playlist later tonight. Also, linked is a short survey to help us improve our TVE sessions. Please take a few minutes to fill out that survey and the other short survey to receive credit for attending. Before you all leave, I want to share the TVE sessions that we will have next Friday. At 1 p.m., we will have Makerspace, and at 3 p.m., we will be back with Happy Math Hour. Math 1314 will be covering linear and nonlinear systems, and 1324 will be reviewing for exam 3. Thank you all for coming in today. We hope you all have a lovely weekend. If you guys have any questions, feel free to use the chat box or your mic, and we hope to see everyone again next week. Bye, everyone. Thank you.